So today we're learning about something a little different, different than line graphs. We talked about them not being linear the other day, about how they wouldn't have a constant rate of change, no slope, and they're going to look like what we see today. So here's some examples of quadratic or nonlinear functions. This is actually a cubic function. Here's a true quadratic. It looks like a U. This one's actually to the fourth power, I believe, but just nonlinear. Okay, so on slide 2, we have a vocab word. In the previous lesson, you learned about nonlinear functions. A special type of nonlinear function is called a quadratic function. A quadratic function is a function in which the greatest power of the variable is 2. Its graph is U-shaped, opening upward or downward. So let's complete the graphic organizer by answering the information about the quadratic functions with true or false. If false, give a statement. A function in which the greatest power of the variable is 2. So if we read the definition, that would be true. The graph of a quadratic function sometimes opens upward. It says it opens up or down, so it could be sometimes up. The graph always opens downward. False. It sometimes opens upward. The graph is a straight line. No, it's U-shaped. Well, I guess it's false. Oh, if false, give the true statement. So if this one's false, it opens downward or up. There we go. So now they're all fixed. Okay, so here's just some fill in blanks. You might see these again later. A quadratic function looks like, it'll look like this on the, if you see a formula, it'll be y equals ax squared plus bx plus c. These will be numbers. So it says notice the power on the x. It will always have an x squared. The exponent on the x is always a 2. That's why it makes it special enough to call it a quadratic. The graph opens upward if the x is positive. So if this is like ax, if this would be 2, 3, 4, any positive number. And downward if the x is negative. So if it has a negative coefficient. The graph of a quadratic function is called it looks like parabola, but it's called parabola. This is always U-shaped. We're going to use -2, -1, 0, 1, and 2 for our x values today. So we're adding a value to see the shape a little bit more. So on to slide 4, it says graph this. To graph a quadratic function, make a table of values, plot the order of pairs, and connect the points with a smooth curve. So not a straight edge, but a smooth curve. So I told you which ones it would be helpful to use. So -2, -1, 0, 1, and 2. There are circumstances where these are not the best, usually when you're working with a fraction, but we'll see if we get there. So this one, we plug them in. So -2 squared. -2 times -2 is 4. -1 squared is 1. 0 squared, 0. 1 squared, 2 squared. You should see a pattern here, and that will be true for every parabola. So if we graph this, -2, notice it goes by 2s, so -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. So the left side and the right side look similar. I'm going to kind of connect it with a smooth curve or a U shape. So it looks kind of like a U on a graph. All of them will look like a U. So now this one, we have, let's pick our values, x, y, -2, -1, 0, 1, and 2. So here, you know what? I'm going to make this table a little bit bigger. What I'm going to do is I'm going to write my work in the middle column. We've done that before. So this is -2 squared plus 4. So this is 4. -4 plus 4 is 0. Negative times -1 squared plus 4. Negative. So this is 1. Now it's -1 plus 4 is 3. -0 squared plus 4, well, 0 squared is 0, plus 4 is 4. 1, so -1 squared plus 4 is 1. -1 plus 4 is 3, which is what we're happening up here. And 2, negative times 2 squared plus 4, -4 plus 4 is 0. So there's that pattern again, which this is kind of like the y-intercept, which is where it starts. So we'll see that here when we graph them. -2, 0. -1, 3. 0, 4. 1, 2, right? graph might not be the right graph. We'll just estimate. 1, 3, 2, 0. Sorry about that graph. It should go up a little farther. So now we connect it with a smooth curve. It opens downward because this x is negative. Okay, so sorry about that graph, but that's a little different. Have you noticed anything about the points, how they look on a graph? There's a U shape. Hopefully this graph will work. So I'm actually going to make an x, work, y, negative 2, negative 1, 0, 1, 2. Okay, so 6 times negative 2 squared, this is 4, 6 times 4 is 24. 6 times negative 1 squared, 6 times negative 1 squared, so 6 times 1 is 6, 6 times 0 squared, 0, and it's going to follow the same pattern as above. Okay, so now we need to figure out what to go by. I'm going to make these go by ones. 1, 2, 3, 4. Okay? But these ones I need to get to 24. So if I go 3, 6, 9, 12, 15, 18, nope. 4, 8, 12, 16, 20, 24. Okay. So negative 2, 24. Negative 1, 6. 0, 0. 1, 6. And 2, 24. Connect those with a nice curve. Arrows at the end. This one didn't have a plus anything, so it started at the origin. This one had a plus 4, so it started at 4. This one opens up because the 6 is positive. Now let's try a word problem. The function h equals 0.66d squared represents the distance d in miles you can see from a height of h feet. Graph this function, then use the graph to estimate how far you can see from a hot air balloon 1,000 feet in the air. So we're working with a little number here. I think we could pick larger numbers. So this is 1,000 feet in the air. So I think maybe we should go by something different. So let's go x, work, y. Let's pick x's of like 100. So 100, 200, 300, 400. We should be good there. And then I'm going to label my x-axis. That should be the d, and h should be the y. So d stands for distance in miles. And the y-axis stands for height in feet. So I think our distance, we can go, I'm going to change this, sorry. Let's just take these zeros off, 10, 20, 30, 40. We can make these, I'm going to go ahead and go by 5 since I have so much space. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. Then I'm going to make these go by hundreds because we need to get to 1,000. So 100, 200, 3, 4, 500, 600, 700, 800, 900, 1,000. Okay, here we go. So if we plug in 10, we would have 0.66 times 10 squared, which is 100 times 66, or 0.66, which turns that to 66. So 0.66 times 20 squared, now that one I don't know. So 0.66 times 20 squared is 264. 0.66 times 30 squared, 594. It won't have a slope, so we can't just add the same amount every time. 0.66 times 40 squared is 1056. So if we graph this, it says use the graph. 10 and 66, so not quite halfway up. 20 and 264. Have to estimate. 30 and almost 600. 40 and over 1,000, just barely. So if we connect these, the smooth curve. We'll see that one. It says, then use the graph to estimate how far you could see from a hot air balloon from 1,000 feet. So if we did our 1,000 feet connected here, and we followed that down, about how far you could see. So I'd say about 39 miles from 1,000 feet. Now, if we wanted to know that for sure, so we're just going to check our work up here. We would plug in 1,000 for h equals 0.66 d squared. And this takes us back to chapter 1 where we divide by 0.66. So 1,000 divided by 0.66 is, I'm going to round to the nearest whole, so 1515 equals d squared. To undo squared, we take a square root. So we would get d equals, I'm going to take a square root of that answer. 38.9, so 39 miles. Graph is pretty good. All right, so there we go. Remember, it's parabola, not parabola. This is my favorite quote, I think. She stood in the storm, and when the wind did not blow her way, she adjusted her sails. Have a great day.